Welcome to the second video in our 13th class time series of lecture videos. We ended the first video by observing that all of the reactions that we considered at the start of that first video proceeded by an SN2 mechanism. That's a bimolecular nucleophilic substitution mechanism, sort of said backwards by the little acronym SN2. Anyways, the SN2 reactions proceed by backside attack of the electrophilic carbon, and they proceed with inversion of stereochemistry. So let's consider S1-bromo 1-deuteroethane in an SN2 reaction. Well, here we've got hydroxide, and our hydroxide nucleophile appears to be, in terms of this arrow pushing mechanism, trying to form a bond with the carbon and kick out bromide. This would be geometrically an example of a front side attack of our nucleophile on our carbon electrophile. It's front side because the hydroxide nucleophile is coming in from the same side as our bromine leaving group is on. And so we'd get a transition state that kind of looks like this, where our bond to our hydroxide oxygen is forming, our bond from the carbon to the bromine is breaking, and we get, wow, S1 deutero 1-hydroxyethane. So the stereocenter did not change in that case. Let's consider the backside attack paradigm, where our hydroxide nucleophile now approaches the carbon from the opposite side of the bromine leaving group. So that's the backside of the carbon. We've drawn an arrow pushing diagram that indicates we're going to use a pair of electrons on the oxygen to form a bond to carbon, and if we form that bond, we have to break this bond. So we'll push those electrons onto bromine. Here's a transition state, and you can see, oh, the hydroxide's got some sort of delta minus charge, the bromine atom has a delta minus charge, and the carbon has an electropositive delta plus sign. And you can see that we formed a different stereoisomer in this backside attack than in the front side attack. In fact, these would be non-superimposable mirror images, otherwise known as enantiomers. So experiments show that you get exclusive backside attack for SN2 mechanism-controlled reactions. In the transition state, the carbon is sp2-like and electropositive in the backside attack. Also, this backside attack paradigm accords much better than front-side attack with molecular orbital theory. So we'll delve into that shortly. It's just a lower energy pathway. So why is the backside attack of the nucleophile preferable to the front side attack? Well, first, negative charges repel. This disfavors the front side. If your hydroxide is coming in from the same side as your bromide is leaving, they sort of experience each other's presence, and that raises the energy in the transition state. Again, frontier molecular orbital theory says we require a specific geometry for a low energy reaction to occur with more optimal orbital overlap. And so the highest occupied molecular orbital of the nucleophile interacts with the lowest unoccupied molecular orbital of the electrophile. That overlap is a little better in the backside attack paradigm. Let's just look briefly at the thermodynamics for the reaction. What are we really doing? We're breaking a carbon-bromine bond, and we're forming a carbon-oxygen bond. So, you know, how much is that carbon-bromine bond worth? 70 kcals per mole. What's the carbon-oxygen bond worth in methanol? Oh, apparently 94 kcals per mole. So we should be getting heat out because the bond formed is much stronger than the bond broken. And, you know, for the 20 years of my life that I've been running reactions, Most of them have been enthalpically driven, that is, they are spontaneous because they release heat. And particularly SN2 reactions are pleasant because you can usually put your hand on the round bottom flask and feel heat coming out of it as the reaction proceeds. So that's because of relative bond strengths. So we would not prefer spontaneously to go this way. And we'll talk about, what makes a good leaving group. So bromide is obviously a better leaving group than hydroxide in terms of, relative basicities and such. So one last page to consider, and let's look at the molecular orbitals, because I did promise that we would consider the molecular orbitals involved in this. And so here we have a molecular orbital diagram for hydroxide. We notice that there are 3 lone pairs on oxygen. We obviously must have an oxygen-hydrogen bond, so we have a sigma OH, a sigma star OH, and then a bunch of non-bonding pairs of electrons on oxygen. And so because the non-bonding orbitals go in between bonding molecular orbitals and antibonding molecular orbitals in terms of energy, our highest occupied molecular orbital will be a non-bonding pair of electrons on oxygen. How about the molecular orbital diagram for methyl bromide? Well, we have 3 carbon-hydrogen bonds, so that means we have 3 sigma CH molecular orbitals, and if we have 3 sigma CH molecular orbitals, we must have 3 sigma star antibonding carbon-hydrogen molecular orbitals. We also have a carbon-bromine bond, so we must have a sigma CBr molecular orbital. And if we have a sigma CBr molecular orbital, we'll have a sigma star CBr molecular orbital. And then, of course, we have 3 lone pairs on bromine, which I have not explicitly drawn, but I know that you know that they are there. And so we put those non-bonding pairs on bromine in the middle between our bonding molecular orbitals and our antibonding molecular orbitals. But wait, Dr. Wagner, why are the sigma carbon-hydrogen bonds molecular orbitals lower in energy than the sigma carbon-bromine molecular orbital? Well, that's because the carbon-hydrogen bond is made up of a C-sp3 hybrid overlapping with a hydrogen 1s orbital. That's a lower energy combination than a C-sp3 hybrid overlapping with what would bromine use for its bond to carbon. Well, it comes in the periodic table after chlorine, which is after fluorine. Fluorine, we're filling 2 P's. Chlorine, we would fill 3 P's. So the bromine would use a 4p atomic orbital, and so a carbon sp3 hybrid overlapping with a 4p orbital is a very high energy combination compared to an sp3 1s combination. And then we also looked at, what's the dissociation energy for the carbon-bromine bond, and I believe we saw it was 70 kcals per mole, but we also know that a carbon-hydrogen bond is worth, around 103 kcals per mole. So, a much stronger bond. So yeah, we would expect it to be lower in energy than our sigma carbon-bromine bond. Anyways, the lowest unoccupied molecular orbital for our molecular orbital diagram of methyl bromide is the sigma star antibonding carbon-bromine molecular orbital. So that's the orbital that can take electron density. So obviously, when hydroxide bumps into methyl bromide, it's going to put its non-bonding electron pair into the molecular orbital that can most easily accept it. That's the antibonding molecular orbital for the carbon-bromine bond, and that has the effect of breaking that carbon-bromine bond. So there we go. This is what we're symbolizing. This is the sigma bonding carbon-bromine molecular orbital. obviously where the lobes are sp3 hybrid is overlapping with our 4p-like lobe. Here is the sigma star antibonding carbon-bromine molecular orbital, and we have a light phase lobe between the carbon and bromine nucleus, and it is confronting a dark phase lobe on the bromine, and so we can't overlap oppositely phased lobes. They cancel each other out. It's arbitrary whether we chose the white lobe on carbon and the shaded lobe on bromine. We could equally well have chosen the shaded lobe on carbon and the light shaded lobe on bromine. Those are antibonding combinations. We get a node between the two nuclei. And so there's a perfect geometry for backside attack. Our non-bonding pair of electrons in our hydroxide in its lobe can overlap with, the similarly phased lobe on carbon on the backside, and that pumps electron density into the sigma antibonding carbon-bromine molecular orbital, which has the effect of breaking this bond. And then this kind of looks like a sigma carbon-oxygen molecular orbital, does it not? Anyways, this video has gone on a little too long, but I think that pretty much does it for our Class 13 time series of videos. I'll see you at the next class.